All right, here's our last installment for our week 6, chapter 6 kind of video. This one's going to be about polarity, so there's going to be a lot of nice review from our previous chapter where they started to talk about bond polarity. This is going to talk about polarity relative to shape. So we still worry about the bonds, but then think about how do those bonds work together? How do they work against each other to make the overall molecule polar? So some definitions that we would have had in that last chapter is really that 0.5 or larger. So when you do the subtraction for electronegativity, you really have that 0.5 and larger. That's what we call polar, all the way up to about 2. And then anything less than 0.5, we call that nonpolar, all the way down to 0, which would be the obvious nonpolar because there's no difference whatsoever. But up to about 0.4 is really what we see a lot of examples with hydrocarbons being 0.4 being the difference between carbon 2.5 and hydrogen 2.1. So as we look at these examples here, notice hydrogen to hydrogen. Here we have an atom of 2.1 attached to 2.1. So 2.1 here on hydrogen, 2.1 here. So the tug of war between those two atoms is equal. This is what we would call pure sharing or pure covalent because there's no bully. They have to share equally because they have the same electronegativity to the same atom. However, when we replace a hydrogen with a chlorine, now we're taking 2.1 and then comparing it to 3.0. This bully system means that the electrons are being pulled towards the bully. And we call that a dipole arrow. That'll help us understand dipole forces later because in order to have dipole forces, you have to have dipole arrows first. The electronegative atom, notice, feels partially negative. Electronegative feels negative. That should be kind of a no-brainer. And then if you're getting bullied, your electrons are getting pulled away, but your positive protons are still left behind, and that's going to make you feel positive. And what's unique about that is positive atoms can attract other partially negative atoms. And partially negative atoms can attract other partially positive atoms. And now we're starting to see molecules pretend or feel like metals that have positive and negative cations and anions, respectively. So this is molecules cheating to feel positive, to feel negative when they don't have real losses and gains of electrons. But they are, in some cases, getting very close for that to happen. So again, when we look at molecular polarity, what we're looking at is bonds first and then shape second. If your bonds aren't polar, you don't have to worry about becoming magically polar as a result, because if your bonds are nonpolar, you're going to stay nonpolar, and that should be a no-brainer. The disadvantage is if you have polar bonds, some of those polar bonds can cancel in their shape, in their direction of their shape, and that can leave you overall nonpolar, and that's what we have to worry about. So in these situations, we just have two atoms. The bond itself determines the shape because they're linear. They're two atoms like we'd expect from our previous videos. And when we see the difference here in electronegativity, we notice that these are both polar, and the reason they're both polar is they both have larger than 0.5 electronegativity differences, and they have an overall direction, in this case, towards the bully of fluorine, which is the biggest bully on the entire periodic table at 4.0, and then chlorine that's tied for third with nitrogen also being a bully. So they both have strong dipoles towards their bullies, and that's exactly what we expect for a molecule that would be polar. So as we start to see polarity through shape, linear molecules will be fairly easy because they typically have one direction. If there's just two atoms, that's going to be the case. But as we start throwing in steric numbers of 4 or 3 or 2, we have to worry about, as a result of their dipoles, as a result of their polar bonds, do any of those polar bonds cancel? If so, do they cancel perfectly and equally? And if that's the case, they become nonpolar as a result. So this is all about dipole moment. So as electrons move in the direction of the bully, do they cancel with other electrons that are moving in that similar fashion? So from these examples here, we can see that oxygen itself has an overall dipole that pushes towards the oxygen atom, and that's because each small dipole is headed in that overall direction. And notice that's also where oxygen's lone pairs happen to reside, making it even more polar because of the extra electrons on the outside of oxygen in that position. So water itself, very polar, and we'd expect that because hydrogen is only a 2.1 electronegative atom and oxygen is a 3.5. That's a big difference of 1.4 on each of those dipoles. That's what we would call superpolar coming up. Over here with this dichloroacetylene molecule, notice this triple bond in the middle here, perfectly nonpolar because you're carbon attached to carbon. But as we go to chlorine out here, we have something unique happen. We have a tug of war in this direction of 0.5 and in this direction of 0.5. So polarity is a lot like a tug of war. We're just worried about who wins the tug of war. So if somebody's pulling to the left at 0.5 and somebody's pulling at the right at 0.5, and that's because the electronegativities are 3.0 versus 2.5 for those atoms. Who wins? And the answer is nobody. So in this situation, we would say nonpolar because 0.5 to the left and 0.5 to the right is a two-way tie. And that's what we have to watch out for a few examples. So vector addition sounds scary, and it probably is. I don't know that I ever did it in geometry class, maybe in high school. The reality of vector addition for our class, though, is you don't have to know much geometry. You just need to know, is it perfect or not? So if you're perfectly left versus right, the same, but opposite, that's going to be nonpolar. Anything else is going to be polar, and that's good enough for us. So recognize perfect cancellation from imperfect cancellation, and you should be pretty safe on most of these examples. So notice in this situation here, we had that 0.5 to 0.5, so our dipoles canceled perfectly. That was 0, that was nonpolar. Even though it had two polar bonds from carbon to chlorine, it ended up being a nonpolar molecule because the overall result of those dipoles cancel each other perfectly, and that's what we have to watch out for. This is not the case for water, but if you drew water incorrectly, you might think that it could be. So here's that trap that students fall into. If you draw water and forget about its lone pairs, you may look at it and say it's kind of linear, where it's not. It's definitely bent. But again, this was just the mistake that a lot of students start to make. They compare electronegativities of 3.5 and 2.1. They start drawing dipoles of 1.4 difference here, 1.4 difference there. So it's almost like they pass each other up and look like 0, right? Well, the only reason they look like 0 is because you forgot everything that I told you, which is unfortunate because those lone pairs are so huge that they actually make those hydrogens pinch together. Those lone pairs forcing them apart, and those dipoles really reinforce each other by their shape towards oxygen, making that very negative and these hydrogens very positive. So watch out for incorrectly drawing shapes. That's why we get practice in this chapter, because if you forget about lone pairs, you're going to forget about a lot of ideas behind Vesper theory and get yourself into a corner where there's going to be a lot of wrong answers because you're not thinking about the most important feature, and that's lone pairs. So let's try an example, PCl3. So in PCl3, again, we're going to do the Lewis dot structure first. That's always the first thing we want to try. So again, let's try to do it symmetrically. So put phosphorus in the middle, 3 chlorines symmetrically around it is usually pretty safe. Remember, halogens on the outside, they only share once. Phosphorus is going to share multiple times, so put it in the middle. Step 2 would be find the valence electrons based on their family. Halogens are in group 17 or Roman numeral 7, so give them 7. Aim the single towards the middle so it's easier to share and connect. And then phosphorus in group 15 has 5. Again, those single dots around to easier connect. Connect the single dots only. And then when you look at this structure, think, does it look like a 3-way tie, or does it really have this fourth kind of direction up. That's where most students get stuck. Definitely looks like there's a chlorine here, chlorine here, chlorine here. Does it have that fourth direction? That's a big difference, because that's the difference between the tetrahedral category and the trigonoplanar category. Once you realize that, yes, it does, because this is a lone pair that is huge, that's your fourth category. And specifically, phosphorus is in the nitrogen family. Phosphorus in the nitrogen family, we'd expect the nitrogen family with 3 bonds and with this massive lone pair that we just tend to snuggle in close just by, laziness more than anything probably. This is exactly what we expect for the pyramidal and the 109.5 shrunk to now 107. And that's what we see there. So what about shapes? This is old kind of ideas here, thinking about Lewis dot structures, and I'm now thinking about a little bit about shape. Remember, in the scope of shape, it's probably the case that this is a wedge going forward. This is kind of a dotted dashed line going backwards. And here's our kind of pyramid-like structure that we'd expect for this type of family, and that's all because that lone pair matters. Now we look at electronegativity. Electronegativity is based on the periodic table, and you get one of those on the back. It always goes up towards fluorine. Fluorine being the third biggest bully tied with nitrogen. So it's in a kind of two-way tie, although nitrogen's 3.0 makes a bigger difference because it's spread over a smaller atom. So 3.0 means a lot more if you're smaller than if you're bigger. And then phosphorus at a 2.1 in the center. So ask yourself, is that difference larger than 0.5? If so, it has polar bonds, and that was a huge portion of our last chapter. So it does. And if it does, it has a direction towards the chlorine, because it's the negative, in this case, electronegative atom, and that's at a 0.9. We also have a pull to the right at 0.9, and the pull kind of down at 0.9. So if you were to misclassify this as a trigonoplanar-like shape, you might think that a 0.9 to the right and a 0.9 to the left does cancel, and it would if it were linear, but this is not linear. Even with a third direction, a 0.9, it could cancel if you knew the right bond angles of 120. But because of the lone pair, that's our fourth direction, and that means all of them go towards the 3 legs of the stool. So all of them go, in this case, kind of in that down direction. So straight down. So underneath, this molecule feels partially negative because it has 3 negative bullies. On the top side, this atom actually feels positive, and notice the positive is always next to the positive end of the dipole. So the arrow is pointing to the bully, and all those bullies are pointing down. So this ends up being a very polar molecule as a result, and that's through its polarity down that matters. So really got to worry about shape, and then how shape affects the polarity of those bonds. Your homework gets a little repetitive, which is good and bad. The good news is these 3 examples are ways to recognize the rule breakers, because they're used in just about every example. So the reason that CO2 is a rule breaker is because if you have a double bond right and a double bond left, there's a 2-way tie. The reason that there's a 2-way tie is because if you pull from carbon to oxygen equally, left and right, this is 3.5, 2.5, 3.5, and that's a 1.0 to the right, it's a 1.0 to the left, and that's a perfect tug of war that nobody wins. So when that happens, it's a 2-way tie, and you end up being nonpolar. And that's why CO2 is about 3 times heavier than water, but still a gas at room temperature. And that's because it has no attraction to other CO2 molecules, because it's not polar. SO3, very similar, but different because of its shape. It's not linear. In this case, it is trigonoplanar. It's going to have a double bond and 2 single bonds. It's going to have those 120-degree angles we'd expect for trigonoplanar. And very similar in electronegativity, Sulfur is a 2.5, oxygen's a 3.5, 3.5, 3.5. Tug of war this way at 1.0, tug away this way at 1.0, tug away up at 1.0. Nobody wins. That's a three-way tie, and it too is nonpolar. So anytime you have a two-way tie, or now a three-way tie, you can have perfect cancellation. It doesn't happen often, but it does happen with these examples, and these examples are in the homework and the exam a lot because of that. Lastly, carbon tetrachloride uses a firebomb, sucks all the oxygen out of the room so it can kill a fire even though it's extremely flammable. So here we have our two flat atoms, to chlorine to carbon, and then we have the wedge forward chlorine, and then we have the kind of dotted line backwards to chlorine. There's the trigonal, or tetrahedral shape of carbon tetrachloride because it has four atoms. It's in that category of four. Looking at electronegativity, we see 3.0s out here on the edge. And then we have that 2.5 in the middle. So you pull up at 0.5, you pull left at 0.5, you pull right at 0.5, and you pull down at 0.5. Nobody wins because all those pulls, all those tugs of war are equal. And if nobody wins, you end up being nonpolar even though you had four polar bonds. So these are the most widely used examples where you have this 2, 3, or now 4-way tie in order to recognize nonpolar molecules but having polar bonds along the way. The reason we care about any of this as we get to exam 3 is to understand that the attraction between molecules is what holds the world together. So anytime you have superpolar molecules attracting superpolar molecules, the partial negative of one attracts the partial positive of another, and that attraction, that's the glue that holds the world together. So you can imagine that here's your head, here's your, Tylenol. The attraction between it and your inflammation in your brain, that's a partial negative to partial positive attraction. So that ability to attract, but also have the right shape is what medicine, is how medicine works. The ability for that attraction is getting you in the right organ, getting you in the right position, the right tissue, the right, surroundings. But then having the right shape is like the key fitting into the lock. And if both the key has the right shape and the right attraction, it can help soothe some of those symptoms in many cases. Not all keys fit perfectly, and we'll see that as the chapters come up. So there are side effects to some drugs because they can accidentally fit in other spots where they're not supposed to. But just notice that this is a hierarchy of kind of glue that we're going to talk about coming up in the next several chapters. It all goes up. Hydrogen bonding is the strongest superglue. It's what happens when you pick your 3 biggest bullies on the periodic table and you attach them to the biggest wimp, hydrogen. Those dipoles are so huge that you're going to have some very strong partial positives and negatives, stronger than all others. If you're just polar but not the special kind of polar, then we have these dipole forces. And again, if you have a dipole force, you're going to have a dipole arrow. You have to be polar in order to have those. And that's what water has. It just has a very special kind of dipole. So hydrogen bonding in a way is just a super dipole force in a sense. It represents kind of the normal glue, like a Elmer's kind of glue. It's pretty strong, but just not the strongest. And we'll focus on it in another chapter later. And then dispersion forces are the weakest of all forces. It's what everything starts with, and then you just kind of tier yourself up this category depending on the kinds of bonds you have. So everybody starts down here, and then it's just a matter of how much do you have, and it all depends on the atoms that you have. Everybody has the weakest forces to start because they have electrons that can move around and have a little bit of attraction just by having a lot of electrons that can shift, disperse around the atom. And then if you have the right kinds of atoms, you can have dipoles. And if you have the specific 3 types of atoms attached to hydrogen specifically, then you can have the best of the best. And that's hydrogen bonding. So we're introducing these now so that we can focus on them in a later chapter. And it'll turn out to be about 3 chapters after this one. So we'll see you then.